Okay, good afternoon, everyone. Welcome to another session of about AI and deep learning. So today we'll see a couple of techniques that you can actually use to build your own computer vision or actually any sort of AI system with very little amount of data that you have, very little amount of test or training data that you have, and still achieve pretty good accuracy and performance. So today we'll quickly go through about what's deep learning and how it relates to computer vision and what are its capabilities and all, and we'll go through the problem of having test data, that the problem that everyone building AI systems is going through always is having not enough training data, and how does that contribute to the models you are building. And we'll look into one of the solutions which is the concept of transfer learning in AI, which is one of the solutions to this problem, and one that you can achieve yourself and you start building your own AI systems. So to start off, let's quickly go through a little bit of history and see what deep learning is. So can anyone tell me what deep learning is and how it relates to the terms AI or artificial intelligence and machine learning? So basically there is an idea called intelligent machines. The idea states that one day machines will achieve intelligent behavior. So what's intelligent behavior? It's still a little bit of a vague term, but we consider certain behaviors that exhibit in living beings as intelligent behaviors that the machines still can't perform. So the idea of intelligent machines is that we can one day build machines that can emulate or process such intelligent behavior. So for example, vision or giving meaning to a visual input is considered intelligent behavior, and machines are starting to get to the level of intelligence of humans right now in that area. Another area that we consider intelligence is language. Machines are still struggling in that area, but there have been certain improvements in that area as well. So based on this intelligent machines concept, the idea, there's a formal research field to actually build such an intelligent machine one day, and that research field is called artificial intelligence. So artificial intelligence has many different sub areas and branches and approaches that people have come up with over the years. One of them is called machine learning. Machine learning is of course a subset of AI, and what machine learning does is it aims to provide machines with the ability to learn by themselves. So in some areas of artificial intelligence, the researchers are working on building an intelligence from scratch. That means programming in intelligence. For example, expert systems, rule-based expert systems are AI but not machine learning. Machine learning is you build the algorithm so that the machine can learn itself. The perfect example is artificial neural networks. You build the algorithm, you give the training data, and the machine itself learns. Now, from this machine learning concept, over the past 8-10 years, due to the advancement in the computer processing power and all, a new subset of machine learning has emerged called deep learning. Now, deep learning is based on the same concept of machine learning, but because of how our understanding of how the human brain works has advanced over the years, deep learning is capable of achieving much more than traditional machine learning algorithms, because it uses a concept called hierarchical feature learning. So, as you can see, deep learning is a subset of machine learning which uses hierarchical feature learning, and machine learning is itself a subset of AI, and all of these are trying to achieve the ultimate idea of building intelligent machines. So I talked about deep learning and hierarchical feature learning. So what's hierarchical feature learning? So our brains, human or even other living beings, as we have found out, that when presented with some data, some input, doesn't process the entire thing at once. The brain tries to break the input into smaller manageable pieces, try to understand the features or any patterns in those smaller features, and then progressively look into the bigger picture, the full input, using those smaller patterns that the brain has identified, and try to build the big picture progressively, iteratively. So this is called hierarchical feature learning, and this is the thing that separates deep learning from everything else, because deep learning also uses hierarchical feature learning. It tries to break down the entire problem, entire input into smaller pieces and identify the patterns from it. So let's look at a quick example. I think forgot about that. So this is an example of deep learning computation model. So as you can see, when that particular input is presented to the deep learning model, it doesn't go and try to process the entire image pixel by pixel. It breaks it down and try to identify smaller primitive features in the image, smaller patterns first. Once it identified these smaller patterns, so these ones, it tries to build the next level of features that it can identify using the smaller features that it originally looked into, and then more high level features are identified, and so on until the entire thing is until the model can give a meaning to the entire input image. So you can see that it's a iterative or step-by-step process, and after the feature extraction, we usually have some sort of a classification model or an identification model based on the features that we have identified. And any questions so far? Okay, so what about computer vision? Deep learning is not just computer vision, it's just one of the fields that deep learning is working on. And do you know what's the difference between normal image processing and computer vision? Image processing normally means we manipulate or do some things to the images so that humans can identify them or get some meaning out of them. computer vision is the field where you process or do some things to the images so that machines can identify them. So deep learning works exceptionally well in the computer vision field because vision in living beings work with the same concept of hierarchical learning, and since deep learning is based on hierarchical learning, it performs really well. So and when we are talking about recent advancements in computer vision, we should definitely mention the Imagenet project. It's actually started in 2007 with the goal of giving a complete image dataset for researchers to build their AI models on. And the good thing about Imagenet is they have a competition that runs annually called the Imagenet Large Scale Visual Recognition Challenge, and it's sort of like the Olympics of the AI world. Every serious researcher tries to compete in this and win that year's prize on it. Because of this challenge, there has been many new and exciting machine learning, deep learning models have been published, and research community as a whole has been able to achieve accuracies that were not achievable a couple of years before because of this competition. So if I go to a little bit of history, around 2012 is where the deep learning, the true deep learning models start to emerge. In 2012, a model named AlexNet won that year's prize. It had an error rate of 15.4. That means of all the inputs given to it, it was able to only 15.4% were misclassified by the system. The others are suspect. In 2013, a model called CFNet, and the error rate dropped to 11.2. In 2014, it dropped to 7.3%. In around 2015 and to this year's competition hasn't been started yet, but since last year, multiple models were published, and by start of this year, it's estimated that around 600 new deep learning research papers were published every day. So after 2015, I can't even draw the timeline because it was so much of new development was made, but let's look at 2015. Within 2015 itself, 3 major models were released, and the error rate dropped to 6.7 to 3.6 to 3.46. And biologists say that the human image recognition error threshold is 5 to 10%. That means these models have achieved superhuman level intelligence in image recognition, and that's only in 2015. So just guess how it would be right now. So because of the popularity of these models and how well they are documented, many machine learning frameworks out there has these models built in so you can experiment with them freely, and even they have the trained model there so you can observe how they behave. So so if I give you an example, one of the more popular and widely used framework, deep learning framework called Keras, has if you want to build one of these models, you just need one line basically. So let me show you how quick demo on one of these models. So I have here a couple of images. Let's see what if we put one of these images through Imagenet model and see whether it can recognize the recognize the image. It identified this image as a sports car with 97.9% confidence. See, so, and if you can see some other categories that it was able to predict using this image, and as you can see, all these other categories are still related to the image. That means basically this system has identified the meaning of this image. So let's see something else. Still, even the confidence is a little bit low, but it has identified it, even the subcategory up to subcategory level. So, as you can see, these models, these widely available models, are capable of very accurate computer vision tasks. So that's
you need to train them.
These ones are already out of the box trained, and you can get the trained model even, and you can retrain them as well if you need it.
How does the confidence level is derived? How does the confidence level is derived?
So based on the computer vision, the deep learning model, in the deep learning model, there's in the last layer you have an array of classes to the classifications that you have trained the model. So in those classes, you when you categorize an input image, you apply a mathematical operation called softmax. It selects one of the categories as the highest possibility, and based on all the categories and the input weights coming in, it assigns a confidence value there on how the model thinks how confident that category is the one that is the one that's correct. So that's the confidence value that we are getting here. So that's the model's identification on how confident in the result it has given. Any other questions?
Is
Yep.
the AI running behind that model?
Sorry?
Artificial neural network is running behind that model?
Sorry, I can't really
Is
hear
there
you.
any artificial neural network behind running?
Exactly. It's a specific artificial neural network called a convolutional neural network that is running behind this.
a mix of
A mix of images. It will try to identify. So since these models were trained to output a single category, it will try to identify the most prominent one that it can identify, and then then give that category as well. There are other models that are called object localization models that are capable of identifying multiple objects within the same frame. So these ones are single object ones. It will still give an output to the most prominent one that it can find in the frame. If you use an object localization model, you can get almost all the categories of it. Any other?
any object localization models like pre-trained models?
There are. I think one of the most recently published one and one of the most easiest one is there's one called YOLO detection. It's you only look once model. It's I think they released their third version only a few weeks back. So that's one of the very new object detection models out there, and they are actually giving out the pre-trained model as well. You can use it directly. Other ones are there's a set of models called RCNN models. Those are also used for object detection.
And how to select the especially we need to predict the rainfall.
Mhm.
In the profit.
Mhm.
Right? How can we select the model right now? There are plenty of models that we Ariba model and Keras is one of this,
Mhm.
and we use TensorFlow also.
Mhm.
So how to select?
So TensorFlow, Keras, and all those are frameworks. They support multiple types of models that you can apply into different subject matters. So, for example, convolutional neural networks works best with classification and more specifically classification of images. You can so something like more continuous values. So the rainfall example you mentioned, that would require a regression type model. So different types of models work best with different type of problems. So move on. So now you've seen how even a couple of years old deep learning models work so well with image recognition. And you might be thinking, okay, can I build something like that on my own? You can, but that's where the usual problem comes in. Do we have enough data to train it? The Imagenet models, although they work pretty well with, as you can see, over 90% confidence in some classifications, they were trained with over 14 million images. And practically, if you are to build something your own, you don't have 14 million images. So should we just give up and leave it to the other researchers? Of course not. There are methods that we can build as accurate models with the concepts available in deep learning, and transfer learning is one of them. And we are actually reusing some of the work done by the Imagenet models to train our ones. And if you're wondering what's the problem with insufficient data, it's a fairly common issue called overfitting. Now, think of a deep learning model as a person who doesn't know anything to start. If you only show them a few images and say this is a car and So if I take that car image I showed earlier and tell them, okay, this is a car, and only show that one, he will start to believe that, okay, a car should be red always. It should be this shape. So that means that model has been trained, but it's trained to just the few data points that you have given. That's called overfitting. Our target in machine learning in general is for the model to generalize more. That means using the training examples that we give the model, it should identify the common features of the training dataset and then apply that knowledge to other new data that is coming in later on. So without sufficient amount of data, they still can't achieve that. So that's the problem of having a small amount of data to train your models. So one of the simpler solutions that we have for this matter is called data augmentation. That means we take one input, we apply a set of random transformations and basically tricks the model into thinking there are more training data coming out of it. So this is a single. So this example is a single image augmented in randomly augmented in many ways. So if you instead of that single image, if you put these things as the training data, since it's not the same thing repeatedly it's training on, the model will start to look into patterns rather than the actual image. So that is what we are after. You don't have to, if you want to apply data augmentation, you don't have to do it manually to each image. There are functions built in to those frameworks I mentioned to automatically augment data and try to make them, even though we have a little amount of data, it will try to make it more and try to more generalize the model. But this is only a limited solution. You can already see you can rely on this alone to make sure that your model doesn't overfit. So the better solution is called transfer learning. So what is transfer learning? Let me ask you something. What are these images? So birds, right? Although you haven't seen any of these birds in real life or any of these images, you know that these are birds. If I ask you, out of these three, select the tropical bird or the bird that lives in a tropical area. None of you have probably seen this, but you can make an educated guess, right? How do you do it? You haven't been trained in these images or any bird image training, but you have some past experience that you can apply to this unknown problem and come up with a fairly accurate assumption on what the correct one is the center one. So if us humans can use that past experience and apply it to a unknown problem that we haven't encountered before and still come up with a fairly accurate result, since deep learning models are based on human brain, can't it use that same method? So that's the idea of transfer learning. We have models out there, like the one I showed earlier, that are already trained in some sort of data set. And those are trained with millions of data, and they are capable of their own thing. Can't we reuse them in another problem area entirely? So if we look at deep learning model, as I said, because of that hierarchical feature learning technique that we use, most of the model acts as a feature extractor. It tries to look into the input, the training that we have given it, and it's trying to extract the features or patterns out of them. And only the last bit of the model is the classification or identification portion of it. So that means all the training, all the trained models have in there some sort of features that they have learned isolated from the actual identification. And since all deep learning models work with that hierarchical learning, we might be able to reuse some of the features that they have already learned. So for example, we have, let's say we have a model that is trained to identify faces. Now, because that's a deep learning model, it starts with those primitive features and then identify features within the face and then only identify the faces. If we have another model to recognize cars, it also works the same way. That means some of the primitive features that they have identified may be common. Shapes, lines, those sort of primitive features, and the higher level features are combinations of all those things, right? So that means if we have, say, this model that's working perfectly and we want to build this one, we might be able to reuse some of the learnings from here, put it there and only do the higher level portion. So how do you, any questions so far? Okay, so that's all theoretical, but how do you do it? So basically we first need already trained model, and lucky for us, those Imagenet models and even other published models who are already trained is out there, and we don't need to really worry about what they are trained with, because we only want the primitive features out of it. And what we are trying to do is get those primitive features, and basically those features are its past experiences, right, in that model, and try to reuse those past experience of the model and train it into a new domain. So what we do is we take that same model, let's say actual model might be more complicated than that, but we take that same model I showed earlier, we basically split the model here. So because, as I said, the first portion of the model is the feature extraction, feature identification. The later portion is only the identifier. We don't want the original identifier. It was not trained to the categories that we want. We only want these features. We split the model there, and from there we extract out all the features that we have learned, that model has learned, these are called the bottleneck features. They are named that way because this is the point where the model transitions from feature extraction into the classification. So that's the bottleneck of the model. So these are called the bottleneck features. We still it, we extract it out. We build our own recognition part only. We don't want to rebuild it. We already have it, and we reuse this in our own model to the categories that we want. So a typical workflow. Before that, any questions regarding this? Yep.
So let's think there is a car image.
Mm-hmm.
So how can we merge the bottom parameters from the lens model?
Mm-hmm.
We have to create separate lens model, one lens model, merge model.
You only need a dense model for your categories only. So
we think there's a car image
mm-hmm.
with the bird image.
Mm-hmm.
We have to extract all total image parameters from the car and the bird
Mm-hmm.
separately. And create
So it's technically yes, but it's not as complicated as to actually do it. So I'll explain how we are going to do it. Any other questions? So yeah, so how we do it typically is we take one of the pre-trained models and we basically remove the final dense layers, so the classification layers, leaving only the feature extraction or in this case the convolutional layers remaining. And what we do is we take our data set and run through that remaining layers, only the feature extraction layers. And so we have our training set, let's say different types of vehicles. The original model does not know about vehicles and anything, but we run our data set through, okay, this is Toyota Corolla, this is Ford something, and because that there's no classification layer, what it outputs is that extracted features, the bottleneck features. We save out those features. We then create a new model, a new classification model only. It has number of outputs to the number of categories that we need and all any number of dense layers that we require. For that model, as the input, we run the bottleneck features that we have extracted, not the original data set. So from those extracted features, the new model gets trained to the categories that we want based on the representation of our own data. So in the end, the new model that we have trained is trained to our data indirectly, but reuses all the experiences from the pre-trained high accuracy model. So we won't get the same level of accuracy, but it will be pretty close. So if the Imagenet model was doing 97% accuracy in all the test data that it had, for our data set this could be 90, 95 or something, but with just a handful of training data set, we were able to achieve because we were able to reuse that experience from its past training. Any questions, or did I confuse you further? So that's the entire concept of transfer learning. I don't think we would have time to go through the entire code, but I'll quickly go through it just to show you how it's done. Maybe some confusion might go away, because I think you have to see how it's how it trains, how it performs, to actually grasp the concept. So just to give you an example, this is one of the systems I have built recently. It's a bird image identification system. You can basically, these are the I have many more categories right now than this, so these are the categories that I have trained it for. Let's see, pick one of these. And yeah, it's correctly identifies with 99.99 accuracy. This one also 100% accuracy, well, not exactly 100%, it's probably rounded up, but it's pretty accurate. So this is trained using the Imagenet Inception version 3 model with transfer learning. So I'll go to the exact code of it. So here, and I'm doing some data augmentation as well, but we'll skip that for now. So the entire process works in 3 steps. You have to first save the bottleneck features from the original model. You have to then train the newer model. I named it the top model here. That's your own new classification model, and then finally you can run your own data to predict using the trained model. So basically you create we load the Imagenet, whatever the Imagenet model or any sort of pre-trained model into your code. And there's in many of these, so this is using the Keras framework, and many of the deep learning models out there has an option to basically slice that model from the feature extractions to the classification part. Basically break that apart is included as a function in these frameworks. So you don't have to break the model yourself. You just say that I don't want the topmost layers of the model, and it will just slice it for you. And once you have that model with just the feature extraction layers, what you do is you run your training data set through this model, and basically save the output of each of those training sets. So you take each of your training data samples, run it through it, save whatever the output features that is coming out of the model, save it to the disk. You do it for all your data set, and you do the same for your validation data set as well. And once you have both those files saved. So if I yeah, so here you can see the two the training and validation extracted features for all your dataset saved. Once you have these two files, you can build your own classification model. So this is a fairly simple model that I have built, only 1024 node single layer and one output layer to the number of classes that we want, and number of classes corresponds to these categories that we are training on. And what you do is you load this new model, and basically you load the previously saved training and the bottleneck features for the training and validation data, and you train the new model with those extracted features, not your data set, but those features that you have just extracted. And through that, you implicitly trained your model to your data set, but with the same accuracy as the original pre-trained. And once you have the full model saved, you can just use it as a normal model and do your classifications or predictions using that. Probably what I would do is set up another session on a later date to actually go through this code line by line, because I don't think without actually doing it hands-on you can understand much of the code. So that's the concept of transfer learning, and as you saw, you can build your own high performing, accurate AI models with little amount of data that you already have. You don't have to bother about collecting millions of data points in order to start. You can start with an in my examples, I have even started with just 20 images and still got pretty decent accuracy. So using this technique, I think everyone can start building their AI products. They can start integrating or implementing AI into their products as well. And these examples were done for computer vision. This is not limited to computer vision. Deep learning is also not limited to computer vision. There are other domains that this can be applied to. There have been very recent advancement in natural language processing using these same techniques to model languages, to reuse language features learned from one model to another. So it's a fairly new concept, but shows a lot of potential. So and being a new concept, its discoveries is up to you, basically. All of you who want to jump into the AI madness and start building. So yeah, hopefully I can schedule another session to go through and build a complete system from scratch using these techniques. Hope to see you all there. Yeah, we'll see. And if you, meanwhile, my book on deep learning, which covers transfer learning as well and many other topics, is available in Amazon if anyone would like to go deeper into AI, deep learning, and all those techniques. I have a couple of copies with me also, so if anyone would like, they can buy directly from me as well. So, any questions? Any remaining questions before we close for the day?
Yeah, as it identified, it reduces the time drastically.
Mm-hmm.
And however, when you select the feature extraction,
Mm-hmm.
you said, as I learned, so you have to select all the feature extractions already done,
Mm-hmm.
and then apply your training on top of that. So, any particular methodology or things that we need to worry about in selecting those already available feature extractions?
So, when you're selecting that original pre-trained model,
Yeah.
The more classes it has been trained on originally, the better. So for example, the Imagenet, some of those models were trained on thousands of categories. So that's really good for us.
So, what do you mean by category?
So those ones are originally classification models. So they can identify X number of categories of objects.
Right.
So more of the categories that it was originally trained on is better.
It might have more features
Yeah.
identified.
Because more diverse categories
Yeah, yeah.
means it has seen lot of features
Right.
that some of them which will be relevant to us.
We have used get the model summary and see the feature extraction and
Mhm.
the things in the feature extraction we have replicable as
So you don't have to worry that much, because if you know that the model has been trained on sufficient amount of categories, sufficient amount of features, just running your dataset through that model should give you sufficient amount of extracted features. So that's the good thing about it. You don't have to really worry about what might be in there. It'll filter out what's needed for you. Because it works hierarchically, one step at a time.
Is it expensive that we get one of these already trained models? Now, do we need to pay something?
No, those are published out, free to use, most of them. All the models that I showed you earlier
Right.
in that timeline, all of these are available in their training form. All of these and more. So
And what I'm saying is that they might have trained these models with so many categories and all.
yeah,
So even the trained dataset and all that.
even the raw data set, the trained one, the raw data set, everything is available, made available public. Only thing is the raw data set is about 600 terabytes or something. It's there if you want to load it. But the models, the trained models themselves are not that huge. They are just less than gigabyte level.
So we must download that.
Yeah. And these most of these contributed by our tech giant, the Google Net, of course, from Google. WestNet is from Microsoft itself, and few other newer ones from other tech giants, Apple, Microsoft. All those guys are actually actively researching and actively publishing their findings to the community as well.
So would this apply to other fields like voice recognition and other?
Yeah, so there is a active research field going on about cross-domain transfer learning. That means they say that certain features learned from one domain like computation might be able to reuse in other non-vision domains as well. So it's an active research field. No one has proved or disproved it, but what they say is because of the way the human brain works, even with multiple inputs, it can correlate those inputs. It might be possible. So if some of you were to try it out, it will be a benefit to the community as well. Any other questions? Okay then, thank you for your attendance and thank you for the questions as well. We'll hopefully meet in another session. Thank you.